In view of the ever-new, confusing discoveries that the James Webb Space Telescope is recording in space, there is no doubt in the mind of us Nobel Prize winner in physics Adam Riess that our understanding of the universe is simply incomplete because, in reality, the cosmos simply does not do what our theoretical predictions tell us it should do, and it's expanding much faster than it should according to current cosmology. But what is the mysterious Hubble tension really about? Well, scientists from the universities of Bonn and St. Andrews actually believe that they have now discovered exactly that. But unfortunately, their groundbreaking approach also has a small but crucial catch because it is in stark contradiction to what Isaac Newton and Albert Einstein taught us about the nature of gravity. The James Webb Space Telescope is turning the astronomical research world upside down, but a nagging Webb puzzle may finally have been solved. You have surely heard that the most powerful space telescope ever built has already detected a whole series of early galaxies that appear to be much too large and massive for their point in time, only a few 100 million years after the Big Bang. Unfortunately, our standard model of cosmology is not able to explain the existence of such early galactic heavyweights, but maybe it doesn't have to after all. A new research study has now come to the conclusion that the mysterious red dots are, in fact, not inexplicably massive galaxies at all but black holes, and where most of the observed light can be attributed to growing gravity monsters rather than to countless stars. The bottom line is that there are significantly smaller and lighter galaxies that do not shake our established models to their very foundations. And although this solution to the astronomical puzzle still raises some questions and requires further follow-up studies, it seems that we are on the verge of clearing up the confusing mystery of the supposed universe breakers. Unfortunately, the same cannot be said for another no less serious cosmic problem. As mentioned at the beginning, the expansion of the universe continues to present insurmountable obstacles for experts, and if you like, the foundation for this puzzle was laid around 100 years ago. After all, the American astronomer Edwin Hubble not only recognized that the Milky Way is by no means the only galaxy in the cosmos, but also that the other galaxies in space are moving away from us, a revolutionary discovery which, on the one hand, was accompanied by the realization that the universe is expanding spatially and, on the other hand, that when viewed retrospectively, it must also have had an origin. While that tiny starting point from which literally everything once emerged is now at the heart of the Big Bang Theory, astronomers in the 1990s realized that the universe is not just expanding but that its rate of expansion is also increasing. Dark energy was postulated as the possible engine of this unexpected acceleration, and thus a force that is as wondrous as it is uncharted, which is thought to act as the counterpart to gravity. Why is the universe expanding faster than it should? This, however, immediately gives rise to another fundamental question. How fast is the cosmos actually expanding in detail? Well, although this question may sound quite banal at first, in reality, it represents the core of a full-blown research mystery that experts have been grappling with for several years. On paper, the rate of cosmic expansion is given by the so-called Hubble constant. But unfortunately, this theoretical prediction simply does not match real observations in space. According to the standard model, the Hubble constant is around 67 kilometers per second per megaparsec. A brief explanation. A megaparsec is about 3.26 million light-years, while a light-year is 9.46 trillion kilometers. In other words, this means that the speed at which the galaxies in space move away from each other increases by 67 kilometers per second every 3.26 million light-years. That's an impressive 244,000 kilometers per hour per megaparsec. But it can be significantly faster than that. After all, there is also the value of the Hubble constant, which has been determined with the help of direct astronomical measurements based on supernovae, gravitational lenses, variable stars, or red giants, and which ultimately amounts to 73 kilometers per second per megaparsec. And just to be clear, that's 264,000 kilometers per hour per megaparsec, and thus a whopping 20,000 kilometers per hour per megaparsec deviation from the theoretically predicted value. This dramatic discrepancy is referred to as the Hubble tension. But what could be the cause? Well, the simplest solution would be that the investigations of the past were tainted with falsifying measurement errors, and to put precisely this assumption to the test, the James Webb Telescope has devoted itself to the task of re-examining the data previously collected by the Hubble telescope in the course of new observations. More specifically, the team led by Adam Riess, a Nobel Prize winner in physics from Johns Hopkins University in Baltimore, focused on the datasets that Webb had collected in the last 2 years. Unfortunately, however, this new analysis did not help to crack the mystery of the Hubble constant either, but ultimately only deepened it further. After all, even the analysis of the most extensive Webb dataset to date revealed nothing other than that the universe does not, in reality, do what our theoretical understanding says it should. Thus, the overall result this time also yielded a Hubble constant of 72.6 kilometers per second per megaparsec. And Adam Riess classified this finding as follows. The discrepancy between the observed expansion rate of the universe and the predictions of the standard model suggests that our understanding of the universe may be incomplete. With two NASA flagship telescopes mutually confirming each other's results, we must take the problem of discrepancies in the Hubble constant very seriously. At the same time, however, Riess also emphasized that this not only represents a formidable challenge but also an incredible opportunity to learn more about the cosmos. Regarding the causes of the confusing discrepancies, the astrophysicist can be quoted again as follows. This could be an exotic form of dark energy or dark matter, an error in our understanding of gravity, or the existence of a new type of particle or field. And speaking of a flaw in our understanding of gravity, a research team from the universities of Bonn and St. Andrews recently came to the conclusion that gravity could ultimately behave quite differently than generally assumed, and that this way, it is possible to crack the mystery of the Hubble tension in no time at all. The solution to the Hubble tension? The Milky Way in a supervoid. In a nutshell, the way out of the constant dilemma is that the Milky Way could be in a supervoid, a gigantic void in the cosmos. But to understand what that actually means, we should first consider the overarching structure of the universe. Stars and planetary systems are arranged in galaxies, which in turn combine to form galaxy clusters and can collectively form so-called superclusters. And while experts long considered these superclusters to be the largest coherent structures in the universe, large-scale surveys have shown that they are by no means distributed like cabbages and turnips in space, but rather arranged in a network-like structure. The lattice of this structure is formed by long fibers, the so-called filaments, which can be several hundred million light-years in size. At the same time, however, the filaments also span enormous, virtually matter-free bubbles, and a study led by Sega Mazurenko from the University of Bonn now suggests that the influence of these so-called voids could lead directly to the solution of the Hubble tension. The study, carried out in collaboration with experts from the University of St. Andrews in Scotland, is based on a new observation that suggests that we are, in fact, in a region of space where there is relatively little matter. As an illustration, the scientists compare this constellation with an air bubble baked into a cake, and since the density of matter around the bubble is consequently much higher, gravitational forces emanate from it, pulling the galaxies in the interior toward the edge of the bubble. In terms of the Hubble tension, this means nothing more than that the galaxies are moving away from us much faster than would be expected, so we would simply be dealing with the effects of a local underdensity. This is a perfectly plausible approach, but it does have one crucial catch. Strictly speaking, according to the standard model, there should be no such underdense regions or voids at all. This is because matter should actually be evenly distributed in space. But in this regard, the study authors point to the investigation of another research group that tracked down a series of galaxies 600 million light-years away that are moving away from us 4 times faster than the standard model allows. And if it's up to Pavel Krupa, who also contributed to the Void study, we should not forget that the standard model is based on a theory of the nature of gravity that was established by Einstein, and that it may be that gravitational forces actually behave differently than the creator of the theory of relativity expected. And indeed, the experts used a modified theory of gravity in their computer simulation. More precisely, the so-called modified Newtonian dynamics, MOND, which was developed in the 1980s by the Israeli physicist Mordechai Milgrom and has not yet advanced beyond the status of an outsider theory. MOND describes the rotational behavior of galaxies by modifying the equations of motion of matter and the gravitational field, and thus manages entirely without the influence of the mysterious dark energy. In addition, the alternative theory of gravity also predicts the existence of gigantic empty bubbles in space, and that is precisely the crucial point with regard to the Hubble tension. After all, this would suddenly vanish into thin air if gravity actually behaves as Milgrom describes. In this case, there would indeed be only one constant for the expansion of the universe, and the observed deviations would simply be due to unevenness in the distribution of matter. But this would also mean that, conversely, we would have to abandon the current theories about the nature of gravity. And the question of the extent to which MOND will really succeed in prevailing over the established models is, of course, a completely different matter. And hopefully, the subscribe and thumbs up are on your sheet. We would love for you to become part of our community, so you'll never miss a new video from us again. We'll see you soon.